Another thing that you need to do is when you read this information or you read a popular press article that's advocating for a point of view, or even a reviewer article that's doing that, you have to ferret out the arguments and actually see if those arguments are legitimate. So let's imagine you have found a controversy and both sides are making arguments for and against the topic. How do you tell who is correct? Well, one of the things you can do is use logic, which is a branch of philosophy. And part of that is breaking down arguments, identifying the premises and the conclusions, and then testing them. There's a system they've developed for this. I am no philosopher. I'm a microbiologist. However, I think I've come up with a pretty good formula for going through this and figuring out if an argument is worthwhile and then determining whether it's valid or sound. So let's go through that. Before we do that, I need to define a few terms for you. First of all, premises and conclusions. A premise is a statement that an argument claims will induce or justify a conclusion. And the conclusion is the final statement that is supported by the premises. For example, I've broken down an argument here, which is actually quite controversial right now. Raw milk only constitutes 1.3% of all reported foodborne illnesses in the U.S. Illnesses caused by raw milk is generally mild. The risk of illness from raw milk consumption is much lower than dying in a car accident. Raw milk is the more natural product. Therefore, drinking raw milk is safe. That's the argument. Now, let's see if this holds together. First of all, let's look for missing premises. Sometimes in arguments, people will leave out premises, sometimes intentionally, lots of times not. But these left out or missing premises are really important, especially when you're testing the argument. So in this argument, there actually is a missing premise. There is an assumption that milk constitutes only 1.3% of all reported foodborne illness in the U.S. How'd they get that statistic? They got that from the Center of Disease Control. The Center of Disease Control determines that because doctors, when people come in with an illness that's notifiable, and there's a list of illnesses that the CDC wants to learn about, they must report it, and all that information is accumulated. So they're assuming that the reported foodborne illness rate is an accurate description of all foodborne illnesses. That is a missing premise. Now we want to determine whether a premise is normative versus empirical. We're setting up to then test them. Normative premises will render a judgment of what is morally correct. They can't really be measured. It's more of this is what most people believe is correct. An empirical premise is something that can be observed or measured. So if we go through our arguments here, raw milk only constitutes 1.3% of all reported illness. That's empirical. You can measure that. The reported foodborne illness is an accurate description of all foodborne illness. Again, you can measure that. Illness caused by raw milk is generally mild. Well, that is, I guess you could say it's empirical because you could survey people and ask them if the illness they had is severe or mild. But again, people will have different opinions. The risk of raw milk consumption is much lower than dying in a car accident. Again, you can measure that. And raw milk is the more natural product. This is a normative premise. It's saying that raw milk is more natural than pasteurized milk, and that is something that probably can't be tested. And then there's the conclusion. That is normative and empirical premises. We've identified them. Now we go on to validity. An argument is valid if the conclusion must be true if all the premises are true. There is no alternative. You have to go through and look through each premise, and if you accept each of them as true, is the conclusion true? If you do accept all of these premises, that's good, a good argument or good support that drinking raw milk is safe. Now, there could be other data that's not mentioned, but we're going to say that this is the summation of most of the data that's there, and that if all these premises are true, then you can pretty much assume that drinking raw milk is safe. So this argument is valid. But that's not the end of the story. The important thing is it also sound? An argument is sound if it is valid and all the premises are true. So we've said it's valid, but now we can go and test things. The first one, raw milk only constitutes 1.3% of all reported foodborne illnesses. You can go to the CDC. I went and looked at the numbers, and in fact, yes, that's exactly right. So in period, this is true. The reported foodborne illness is an accurate description of all foodborne illness. That is in fact untrue. People do not report or go to the doctor every time they're sick, especially with gastrointestinal issues, because most of these resolve within a few days and they won't go to the doctor, and therefore it's not reported. Illness caused by raw milk is generally mild. Okay, you could probably kind of measure this, but there's probably no real good data on this. And I'm not sure if it's true or not, but even if we accept that raw milk is generally mild, then what this probably means is that most people are not going to go to the doctor, and it's going to be underreported. So that 1.3%, if you accept the third premise, that 1.3% almost has to be a gross underestimate. The risk of illness from raw milk consumption is much lower than dying in a car accident. Probably true if you accept the 1.3%, but honestly, that's really irrelevant to the safety of drinking milk. It's just a comparison. Finally, raw milk is the more natural product. Again, that's an opinion. That's something that people would have to agree on or morally analyze. And honestly, I don't think that's true. I think pasteurized milk is just as natural as raw milk. You're not doing any massive processing to it. So therefore, drinking raw milk is safe. Because some of the premises are untrue, this argument, in my opinion, is not sound. If you go back and look at what we talked about for analyzing an argument, probably the toughest test is determining whether an argument or a premise is true or not. In other words, determining the soundness of an argument. So here's some tips. Number one, what was the review process for the article in question? If there was no review process, that kind of degrades it a little bit. Now, if it's citing publications that did go through a review process, and that was a rigorous review process, and it's actually representing the data accurately, that supports it more. Secondly, what is the goal of the publication? If the goal of the publication is to just report information, it's probably going to be more sound and more valid. If the goal of publication is to support one side of an argument, then look at it with more skepticism. Secondly, is it even-handed? And does it stick to the facts? Does it present both sides of an argument, or does it only present one? Does it stick to the facts? Look at what's said. Does it say what's actually in the articles it's citing, or does it then go drifting off into opinion and analysis and conjecture from there? Fourth, does it slander any group or use inappropriate language? As soon as you see that, it's using names, it's calling people names, it's using swear words, don't pay any attention to it. And finally, follow the money. Who's paying for this article? For example, if it's an article saying cheese is healthy for you and you should be eating huge amounts of it, and it's funded by the Cheese Association of America, which is cheese manufacturers, then you should probably be very skeptical of the article. In this next section, we're going to be looking at how data is presented. And I've used a very famous quote that Mark Twain used to say all the time, which is, there are lies, damn lies, and statistics. So let's look at some ideas. First of all, we're going to look at statistics, or fooling you with math. One of the things that you should look at is if anybody brings up a rate or a survey of opinions to support an argument, or any kind of set of numbers or statistics, the first thing you should look at is sample size and distribution. First, how big does it have to be? Normally, for something to be statistically valid, you're going to need a sample size of at least 12 or 15 or 20 people or subjects. Now, it depends on how big the difference is between the test group and the control group. But the closer they are, the closer their means are, the larger the group you have to see a statistical difference. The second thing to look at is, what is a normal distribution? And normal distribution is essential for a number of different statistics measures. Now, there's other things that you can do that don't require a normal distribution, but that has to be known. Third, you have to use the right statistical tools. And I'll give just one example, but you can investigate this more on your own if you want. And then finally, correlation does not mean causation. What that means is, just because you see an association between one thing and another thing doesn't mean the first thing caused the second. For example, if people who eat a lot of hamburgers have more heart disease and die from heart attacks, that doesn't mean eating hamburgers causes heart attacks. You have to find the link. You have to find the reason, what in the hamburger is increasing the chances for heart disease, before you can say it's true. It's important to find correlations, but much more investigation is needed to actually figure out what's going on. Let's dig into some of this in a little bit more detail. So here's a data set. You took it, and there's this new supplement called Super Self for muscle gain. It'll make you huge, bro. So you want to use it and you want to test it. So the manufacturer set up a test group, and you have a super sub group here, and here's all the numbers, and you have a control group, and here's all the numbers. And the question is, did the super sub group gain more mass? If you do the averages, you turn out that yes, they did. On average, the super sub group gained 2.66 kilograms, and the no use group, the control group, got 0. If you do a t-test, which is a statistical test between two means, you find the p-value is 0.06. In the t-test, the p-value indicates the likelihood that two samples' true means, what their real means are exactly the same. So that supports the idea that the super sup really works. But let's take this data and graph it. If you graph the data, what you'll see is you have the two groups kind of lining up, except for 3 outliers. This is not a normal distribution. There's 3 outliers in the data, and they pollute the whole sample. So that's what normal distribution means. It's like a bell curve that you've probably heard of or thought about in grading. You want that nice distribution around the mean. And if you don't have that, you can't use a number of statistical tests. And one of them is the t-test, which is used all the time in these kind of analyses. The second thing I want to talk about is fooling you with figures. Graphics can lie, and this is one of my favorite figures. I can't figure out what the heck is going on in this diagram. It's trying to look at subsidies given to various industries and how much. And the way the graph is given, it looks like most of the stuff goes to renewable energy, or half of it. But the graphics that are here have no relation to the numbers. If you look, carbon capture and storage and fossil fuels gets 72.5 billion. That's way more than all the others. So it just doesn't seem to make any sense. Terrible graph. So what I'm going to go through is some more common things. This thing is so outrageously ridiculous, this graph, that no one would take it seriously. But there's subtle things that you can do in graphing data to make it or fool your audience. They are expanding the scale, ignoring the population size, and hiding negative things in a forest of other data. So let's look at those. The first thing you can do is expand the scale. So here's a graphic that was put out by the Obama administration in about 2015, looking at how many students are earning their high school diplomas. And it's saying that graduation rates are increasing, and that's due to the efforts of the Department of Education. Oh, that's wonderful. Well, we've got these little books, and the stack of books increases, and we go from 75 to 82%, and look at that, the stack is huge. This is a giant difference. Or is it? By expanding the scale, this scale, it's not clear where the scale starts. So in fact, these fancy little graphics are kind of fooling with it. I've regraphed it here down on the right. And if I use a scale starting at 0, which in most cases you should, unless you have a really good legitimate reason not to, you'll see that, yes, the bar graph gets a little higher, but there really isn't a huge difference. Now, it's still something to celebrate. You're seeing an increase in high school graduation rates. And maybe that trend will continue, but it's not nearly as profound as shown in the first graph. Another thing that you can do is ignore the population size. Here's a graph of some cities in the United States and the total murders by city. And you'll see that Chicago, there's way more murders. There's 650 murders, which is a horrible statistic. And no other city comes close. The closest one is Baltimore, and it's less than half what's in Chicago. But this is graphing the total number of murders, not taking into account population size. If we regraph that data, and instead we look at the murders per 100,000 people, we find that Chicago is near the same as Atlanta, Washington, Milwaukee, etc. In fact, the most dangerous city is St. Louis per 100,000. And this is a more fair graphing of the data. Finally, another trick that you'll often see is hiding data. Imagine that you started in 2014 at a company and you're the chief financial officer and you're in charge of spending for your company. And you look at travel expenses by year, and you see that the number has risen from 200,000 to 450,000, which is alarming. That's a huge increase. It's over 50%. The CEO is going to be upset with you. You need to somehow hide this data. So what you do is you roll it all into the other expenditures of the company and make this one huge graph that has nothing to do with the point is what spending is increasing. And then you graph it. And in this, while you can still see that the green, which is travel, expands, it's not near as clear how much it's increased because it's within all these other numbers.